And so we can actually kind of generate these data, as I mentioned, from computer simulations to be able to kind of get a much larger data set to be able to base some of these factors on. And so first what we're going to do is we're going to kind of keep the mutation rate completely constant, because we know in science it's important to keep all the other variables constant and only vary one of them so we can really focus on that. And so in this first particular model, we're going to just have the mutation rate be constant at 50%. Meaning out of 10 individuals, 5 of them are actually going to develop it. Whereas the number of hits, we're actually going to vary. So if you look at these 3 graphs that we have down here, we can see the mutation rate is 0.5, 0.5, and 0.5. Of course, we're keeping it constant, but it's the hits that vary. So we have 1 hit here, 2 hits here, and 5 hits up here, which is not really something we could actually get with the cancer cards. And so what you should kind of really be seeing is that the kind of shape of these distributions, of course, this is the incidence of cancer, and so that red line kind of reflects more the lines that we've been seeing of these cancer incidence by age. But the shape of these different distributions as we vary the number of hits really actually stays the same, but they're actually shifting a little bit over to the right. Do you see how they kind of shifted over to the right? And as we increase the number of hits again, it even shifts further over to the right. So in this particular case, if we keep mutation rate constant but vary the number of hits, we're just shifting the whole distribution to the right. That's all we're doing. Another way of looking at this is to just model it out and say, okay, well, let's look at, again, those individuals that are about 25 years old, about 60 years old, and then about 80 years old. Clearly, by 80 years old, it doesn't matter how many hits you have. According to all 3 of these models, every single one of those 80-year-olds develops cancer. So we know this is not a perfect model, but it helps us kind of see the difference. Again, at age 60, every single one of them has it. 100% of individuals get cancer. But it's really the difference we can highlight here is at age 25. And that is that only according to 1 hit, meaning you only have to have 1 mutation and you develop cancer, clearly this mutation rate is going to be very, very high. Whereas it's when we kind of increase the number of hits, we can shift that distribution. So suddenly 2 hits, it shifts the distribution a little bit so that it's actually a far lower likelihood of developing it. And again, even 5 hits, it shifts it even more, less than, it's only about 80% likely. And so that's one variation. Now what we're going to do is we're going to swap those 2. And we're going to actually keep the mutation rate is the one thing we're going to vary and keep the number of hits constant. And we're going to keep them all at 1 hit. So again, you can kind of see here, there's 1 hit, there's 1 hit, and there's 1 hit, and we're just changing the mutation rate. So here is 0.1 or a 10% chance. Here's again that 50% chance, and then here is a 100% chance. So hopefully you guessed that this one, every single individual is 100%. But we see kind of this interesting pattern as we kind of look across these. So this one, there's only a 10% chance of developing it having, or a 10% chance of getting that mutation if you only need 1 hit. And you can see that we have this kind of nice distribution here, that not everyone has it because there is this 10% chance, 90% chance you don't actually get it. But as we shift over, now we have a 50% chance. This is the graph, one of the graphs we already saw. As you can see that in this particular case, we're actually shifting that distribution up. And as we shift again over to a 100% mutation rate, we again shift the distribution up. So it's again the same shape of the distribution, we're just shifting it up, up, up. We can look at it again the same way, looking at the tabular view, and we can kind of get a better picture. So again, we can look at the tabular view and we can clearly see that there is indeed this kind of shift in what we can see here, that by age 80, it was only in these individuals at the 10% rate that actually did not develop cancer. And again, at age 60, you can really see this shift as we compare the age 25, because at the 10% incident or mutation rate, there's only a 40% or 40 individuals, 40% of the people rather, that were actually able to develop it, whereas it shifted all the way up to 100% at a 1 mutation rate equals 1 or 100%. And so we can kind of take all of these ideas and say, okay, well, let's kind of take all these pieces and put them together in one particular subset of graphs. And so you can kind of see that the columns in this particular case, we have 3 different numbers of hits. So the one off to the left is the 1 hit, the one in the middle is the 5 hits, and the one off to the right is the 7 hits. And then we have 2 rows. The top row, of course, is that 10% mutation rate, and then the one down below is just this 0.04 mutation rate. which actually is what we were simulating in our cards, because you had a 1 in 25 chance of developing it. And we kind of look at the shapes of the curves by kind of combining these two different factors and variations of these, and you can kind of see, well, which one is actually going to be the best one to simulate what we're actually seeing in real data. And as we kind of look, it's really difficult to decide which one of these is the best combination to kind of fit that real model of colon cancer incidence by age that we saw at the very beginning of this video. But probably the best one that we actually saw was this one down here, which is 5 hits, meaning you have to have multiple mutations, and this kind of fairly low mutation rate. But in all likelihood, it's probably that the real case is the mutation rate is actually significantly lower than what we actually did or simulated with our model. And that's probably what allows us to get even steeper of a curve and have a lower incidence of cancer, which is probably what we're going to see. But kind of the takeaway message is that clearly you have to have multiple hits. Again, you have to have multiple mutations to develop cancer, and the mutation rate is actually fairly low. So those two combinations of things actually causes this shift, or this pattern that we see in this kind of J-shaped curve, if you will. And so that's what we have for today, is kind of learning a little bit about how cancer comes about and where it comes from.